goes there. Yeah. So kind of I want to recap the whole thing. How we started explaining about that, and hopefully this morning the lab session made it more obvious, is that we kind of talked about how vibration, and in particular how resonance, is going to be used, let's say, for materials characterization. And we looked at a paper together on resonant ultrasound spectroscopy. Yeah. And in that paper, you saw that, and also this morning in the lab, you saw that if you have mass properties or density, and then geometry, and you'll see also boundary conditions. If you have this as an input and you run a resonance test, let's say today you were just looking at one resonance or a few. If you do ROS, you are looking at a bunch of resonance modes. And then you are going to get what? What does ROS gives us at the end? What's the output? What properties? Modulus. Let's call it elastic tensor, because you remember that if you do it right and the material is not very attenuative, you can get the whole anisotropic elastic tensor. I just want you to remember like how we started this. And then some of you, your interests are maybe more related to structural health monitoring. Very similar procedure is used in structural health monitoring to identify defective elements. We looked at the bridge together. And you also saw that it can also be used for looking at, let's say, at a building after an earthquake, like a post-event assessment of structures. You can look at how the resonant frequencies have changed, the mode shapes, and that gives you a global understanding of what's going on in that structure. So these are kind of the motivations of this. And then we started to kind of try to learn about resonance. So very quickly, I want to recap everything we learned in this module. So we started with single degree of freedom systems. And we looked at first free vibration. When we say free, it means that you kind of, like the example we solved, you apply an impulse, or like the hammer that you saw, you kind of disturb the system very quickly, but then you don't continue forcing it. So that's the main difference between using a hammer and using a piezoelectric to do the same thing. In both cases, we are looking at resonance. One is free in case of hammer, the other is forced in case of piezoelectric setup that you saw. And then try to nicely make this organized. Then we have like an undamped system. We first looked at undamped. And of course, this is very simple. This was the equation. So we only have a mass and a spring. And we saw that the solution is oscillatory. It's you can write it as a cosine plus a sine. And we learned that this omega, which is the angular frequency, is related to stiffness of the spring and the mass, and kind of started to understand why resonance is so helpful for materials characterization. And then we looked at the damped system. In particular, we considered viscous damping. And if you remember, we added a dash but here. And we saw that the situation is not as simple anymore, so we need to consider whether the system is critically damped. So we defined the critical damping using a parameter called damping ratio as C over C sub CR. That's for critical. And we saw that if D is equal to 1, it's critically damped, and the response is something like this. And it's not oscillatory. Another case which is similar is when it is overdamped. And we saw that in that case it's also not oscillatory. You get basically two exponentials, but the exponents are real. There is no oscillation. These are important, but not as important as the last case, which is underdamped. It's underdamped, and typically we saw that it's much smaller than 1. In that case, the response was sinusoidals modulated by an exponential. You saw it today. Just remember the curves which were ringing down. So that is, so first I write the exponential. That is kind of responsible for damping. And then oscillation in parentheses, where we can write it in the complex form, like that. So here this is subscript and means that that's the angular frequency of the damped vibrations. This is oscillatory, as you can see, and sometimes we can look at it like this too. So here we can have, let's say, cosine. Make sure that I write this nicely, not to defeat the purpose. And here we also defined the logarithmic decrement, and we saw that you can get it by looking at the maxima as your signal is kind of ringing down. You take two maxima, n and m, and we see that this is related to the damping ratio. So this is something that is being used to characterize damping, logarithmic decrement. I think it's very useful to look at everything at once and see, what the differences are, and you can see it easily like that. And then afterwards we move to forced vibration, and that's when we discuss the accelerometer. So the next or the last part was we looked at forced vibration. It's it's important to distinguish forced and free vibration, because forced vibration is the only difference is that here you have, instead of 0 here, you have some function, some forcing function. So this is not 0 anymore. Just because afterwards I want to discuss the accelerometer, I kind of first write the arbitrary load. So we looked at both arbitrary and harmonic loading. We first looked at harmonic, then arbitrary, but I just reverse it because I want to go directly from harmonic to accelerometer. That's because of that. And in arbitrary loading, I told you that what is important is not necessarily for us, is not all the details of calculation. We all can figure that out. It's more the concept. And the concept that I wanted you to take home with you is the concept of impulse response. So if this is your arbitrary load as a function of time, then if you just look at a very small time increment, it is as if you are summing up the response of all these small impulses. So if you know the response of the system to one of these, to one unit impulse, then you can integrate the whole thing to get the response of the system. This concept turns out to be very important. So basically the response at the end would be a convolution between your forcing function and the impulse response of your system. And this, I showed this by H. So this is unit, that means just unit impulse applying to your system, what would be the response? And in the frequency domain, convolution turns into just multiplication. So it makes everything very easy to solve. And we saw that if the system has no damping, then we can kind of figure out how the response would look like. I write the convolution integral. So for one of these responses, it would be this times the undamped impulse response. Now it's not writing anymore. I don't know what to do. Anyone has experience to see why it's not writing right now? Any? Oh, I don't know what to do. We close, open. This doesn't happen very often. We can complain, but I'm sorry. You mean the battery? The battery is not a problem. I have changed that at the beginning of the semester. No. So you see that it's kind of random situation. I mean, this is a grad class. What I like is when there are 70 undergrads in the class, and then Ryan knows that, right? Sometimes it happens. We can't complain. It's a nice technology. But anyway, for undamped case, we can kind of give a face to this impulse response function, which looks like this. This is kind of easy to see because 1 over n would be like a velocity per unit impulse. And it is like velocity over omega times sine. This is really the impulse response of an undamped system, conceptually. So now, how about harmonic? And that's kind of the or the what we have to look or understand completely if you want to understand the working of accelerometer. So let's look at this a little bit less stressed and less rushed this time together. So if we have a harmonic system, harmonic loading, it means just that PT, the force function, is, we can write it as some harmonic. I like exponential and complex, it makes everything much easier. And in that case, we learned that we can obtain the solution in frequency domain very easily. We took Fourier transform of both sides, and we saw that since the harmonic loading has only one component at one frequency omega bar, that's the excitation frequency, then everything becomes very easy. Then we have the response would be the static response over something which looks like that. We have, it's a function of the ratio of the excitation frequency to natural frequency, and damping is also, of course, involved. This is, of course, the amplitude. So, if you want to see what is the effect of this dynamic loading, we saw that we can actually look at the response of the system and normalize it by the static response. Why do I call this a static response? Because it's just force amplitude over stiffness. That's displacement. If there was no omega bar involved, that's just a static response. And this can be written as a function of, again, damping ratio and this ratio of the excitation frequency over natural frequency, which we call this omega, to just make this expression a little bit friendlier so we understand what's going on. So omega is omega bar over omega n. That's important. And then we also have a phase. And this, we saw that the phase we can also obtain this way. Now, looking at these expressions is not as interesting as when we plot them. So it's very useful to look at these plots. This we called M, dynamic magnification or amplification factor. And this is just phase. Doesn't have a particular name. So if we plot M versus omega, that's kind of an amplitude spectrum. And if we plot phi versus omega, that's kind of a phase spectrum. So a few of you in the homework, instead of phase spectrum, you have plotted the tangent of phase. Well, of course, it looks strange. So phase is actually that angle itself in radian. It's the angle, not the tangent. It's not a big problem, but it's just that phase is an angle. So, now let's look at the plots again and talk about accelerometer. Now a little bit slower this time. I also gave you a copy of the specification of the accelerometer, so we can look at this also together. Everyone has all the notes from this slide. Can I move? I see some people are still. So, fresh from a start. Accelerometer today, you saw it's working. I had brought one to the class the other day also. Inside, basically, there is a mass and there is a spring. There are other elements too, but if you want to model it, there is a housing. So there is a mass, and then there is a spring, and there is a dashpot. And this is the housing. And you saw that today Jiyoung was gluing or using a wax to attach the accelerometer to the surface of, let's say, the aluminum sample or the molar sample. If you use it to measure ground vibration, you kind of place it, you cement it to the ground. It will be much larger. Those triaxial, you probably use geophone, not accelerometer, but it is similar in terms of. So this is the ground. And I use G for anything related to the ground. Now let's see what last time went so fast. What is that? So let's define the coordinates. That's the movement of the mass. I use Z just like before. And this is the movement of the ground. Z sub G. Yep. So now, let's do this again. So you have the mass. The force which is acting on the mass because of the spring is K times the displacement, the relative displacement at both ends of the spring. If the mass of the accelerometer and the ground, they have the same movement, the spring is not going to be stretched or compressed. Yes. So I call this Z sub R. That's for relative. And that's nothing else but Z minus Cg. It's the same for dashpot. Yeah. But the inertia, no, this is the other way around. We took the positive upward, so they both will be against. Oh, what's going on today? Yeah, sorry for crashing the last time you were here. That's interesting. No, press enter. This has never happened before. Recover. Oh no. Okay, you have the... I don't know what to do. I go here. So, anyway, so that's why we had... I don't know what's going on today. Something is with this accelerometer. Every time we want to discuss this, something goes wrong. Either Chaz gives a seminar or something else. Just giving Chaz a hard time. So that's how it looks like. Now, if we write the equation of motion, then we write basically the forces, as you can see here. So we have z dot, zg dot, and this is zr dot, and the other one is z minus cg, as you can see. And to be able to solve this, we cannot have z, zg, everything in one equation. This is not how it works. So we write everything in terms of zr. So this is czr dot itself. This is kzr itself. So what I do is I change z for zr plus z sub g. I can write this again. So if we do that, this m, it will be zr double dot, but then the other part, minus m zg double dot, goes to the other side. Make sure that you agree with me that this is equivalent to the other equation. So far it's really nothing magical about it. Okay? And then let's assume that the ground motion is harmonic. So it has some amplitude and some frequency. And somewhat you all have to be comfortable when we go from displacement to velocity or acceleration. Whenever we go from displacement to acceleration, it becomes negative, and then omega squared will come on the front. Always think in terms of complex exponent. E I omega t. First derivative, I omega, E I omega t. Second derivative, negative omega squared. Think about that, and then you can always go from displacement to velocity and acceleration very, very quickly. So because of that, then we can write immediately the acceleration. But remember that this omega is omega bar. That's the excitation frequency. It's not the natural frequency. Okay, so if we substitute here, the negatives cancel out, and we are going to have something like this. So I delete this here. I hope that nothing happens. I'm so afraid right now. Really didn't want to make the free body diagram and so on again. Okay. So that goes back exactly to what I just reviewed for you. If you have a harmonic loading, that's pretty much P0. So it's kind of an application of a harmonic loading. Okay? So what we want to look at is this amplification M. If you look at the amplification M, you see that it is basically, in this case, ZR omega, right, over P0 over K, which is, this is P0 over K. Dynamic over static response. So here we can write this like that. Yes?
I don't understand the step where you say M Z double dot R plus C single dot R plus K Z R equals negative M Z double dot D. I don't understand that transition.
This one?
Yes. To the next step. that makes equivalent.
To here?
No, this, I don't understand the equivalence.
Then here will be
Yeah.
valid?
Yeah, I don't understand that.
Yeah. So if we assume that this is harmonic,
Mm-hmm.
the acceleration is always negative omega bar Cg. So I'm just, for m is coming here, this is negative omega bar to Cg, and that's E I omega bar T. I make this assumption.
Yeah. So I guess my question is, what happens to those other terms that aren't related directly to the acceleration?
These?
Yes.
Nothing. They're here.
Okay.
This is just the loading.
Okay.
So this is a special case of a forced harmonic. So it's just a special case of forced harmonic vibration. That's why I reviewed this one more time. If we have forced harmonic vibration, and if you take Fourier transform on both sides, from this we can get to here. So we are not changing anything. That's pretty much, it's like an application of that. Here we have T0 kind of has a phase, and that's the ground acceleration. We are not changing anything here. So this is the solution to this equation. M z bar double dot c c r dot k c r equal to m omega bar square z g e r. So what we see here is the solution to that differential equation. So, any other question? So this, we write this magnification factor like that. And then it becomes actually interesting. Because everyone is comfortable with this magnification factor, what it means, and what I'm doing right now here. This is important if you want to solve that homework problem. So my dynamic amplification factor is the dynamic response over the static response. The static response is, let's say if there was no I omega bar t, the system would deform, the deformation would be force over stiffness. Yeah? If you have a spring and you just apply a force, the deformation is force over stiffness. That's why this is the static response. So we normalize it to get this dynamic amplification. That means that because it's dynamic force, the response will be larger most of the time for a smaller frequency. And then all I did here is I bring m here, and k over m is omega n squared. This is something you have to know for the rest of your life, that k over m is omega n squared. And now we are in a situation where we can actually discuss the accelerometer. Sorry about this, but I think this was a pragmatic decision in terms of what to do here. Now, if you want to design an accelerometer, what you want is that what you are measuring is what the acceleration that you are measuring, what you want is that that's similar to the acceleration that is actually you want to measure, right? That's the whole purpose of measurement. You want to measure something, and you are measuring the mass is moving inside the accelerometer. What you are measuring is this z bar double dot. But what you want to measure is zg double dot. So now, how do we make sure that this is the case? Let's bring the omega n kind of up. So this is more like Z bar, ZR double dot, and this is more like ZG double dot. If you want this to be equal, so it's normal that you want to have a magnification factor which is pretty much around 1. So that's why you want to have omega n ZR to be just similar to omega bar squared ZG. This is something you want to have. Oh yeah, that's true. Thank you. That's just to check that you are paying attention. Of course. So for that, we want to choose m which is equal to 1. So now, how can we get m equal to 1? Now we have to look back at these graphs. This is what we plotted m versus frequency. To get something flat, something equal to 1, you need to choose omega, which is a small. You want to be on this side of the curve. If you choose something here, that's definitely not the case. You don't want to be here. You want to be somewhere which is, let me zoom in to make things much more clear. You want to be in this region because this is one, that's m versus omega. To measure, for you to measure the acceleration, you want to have m which is around 1. And this happens in the beginning. That means that, I forgot where I was. That means that you want to be in the region where omega is small. That means that omega bar over omega n should be small. In other words, you want to choose an accelerometer. Remember, this is the system is accelerometer. You want to have an accelerometer which has a large natural frequency. Yes, everyone, this is understandable. But this is not all. So one criteria is that you want your accelerometer has a large natural frequency. Another criteria is that, okay, here if I write ZR, then if that's the case, ZR would be like that, right? Imagine I chose m equal to 1, this is how it's going to be. And imagine that I choose an accelerometer with a very high, let's say, I don't know, a very, very high natural frequency. What happens in this case? What happens is that what you are measuring, let's say you have this coming from the ground, you divide it by something very large, squared. So what you are going to measure will be very small. So you want your accelerometer to have a large natural frequency, but not too large, such that it compromises its sensitivity. If the natural frequency is very high, no matter how hard you vibrate, the accelerometer just shows a little bit of movement. It doesn't even see it. You don't want that either. So these are the principles of the accelerometer. Today, you saw that in the lab that Jiang was connecting the accelerometer to a charge amplifier. Did you notice what the unit of the sensitivity was? Ryan knows the answer. The unit of sensitivity? No. It's fine. No. It's a hard question. What was it? No. No. Oh, what you saw, okay, that's true. What you saw his setting, it was in, how much did he use exactly? In 0.316 microvolt per meter per second. That's true. He didn't probably show you the sensitivity, which is set inside that machine. So for that, we need to look at the sheet that I gave you. So let's see if I go here. It's not going to do something crazy. Every charge amplifier has a sensitivity, and that's in picocoulomb per meter per second per second squared. Coulomb is the unit of charge. It's the unit of charge. And this number is set inside. So if you buy an accelerometer, you need to go through the menus and enter this number into that box. What you saw Jian was changing was not sensitivity. That was kind of the amplification, if you may say that. So if you increase or decrease that, your amplitude is changing, but that's not the sensitivity of the accelerometer. Look here, this is what it is for this accelerometer, which was not working. And look here, what you see here is pretty much the line, the thick line is the M versus frequency. It's the amplification factor. Why it starts at 0 and not 1? It's because it's in dB. So 1 is 0, basically. So as you can see, over this range, the accelerometer M is pretty much equal to 1. Even nicer, you see that they have used parameters such that the phase is also pretty much constant. Right? And this accelerometer has a resonance here. So the resonance frequency is larger, much larger than the frequencies that is being used for. Typically, we use it for up to about 25 kilohertz. We typically even use it for less than that, but that's what it is. And the difference between the left and right is that this is just up to 26, and the other one is up to 100 kilohertz. So you kind of see a zoomed in version to the left. The sensitivity is equal to 1 if you really pay close attention at this point, which is about 150 hertz. So if you are doing a very sensitive measurement and you are not at 150 hertz, you kind of have to correct for that. But we typically don't do for our measurements. The changes are not that dramatic. What else? Here you also see in a specification sheet in what temperatures you can operate an accelerometer. You see the quality factor, remember the Q factor, and you see the resonance frequency of the accelerometer. So every accelerometer comes with a calibration chart which looks like that. And you can always look at it and set up your equipment based on what you see here and decide what you can use it for. Okay? Something also that I noticed that I'm not sure, does everyone here have access to Canvas? And you see that I post the notes in PDF? Okay. Because there is one question in the homework which is in my notes, and someone didn't answer that. That's why I'm checking to make sure that you know. Okay, with that we can, yes. It's when they tested that, when it was being mounted, or if it was just a standalone. It's when it is mounted, is when it is attached to a surface. What we see here, I think, is when it is not, or is it mounted? When it is not mounted, I think. Yeah. No, this. Let me see. I think what we see here is actually the mounted resonance frequency is about 85. Yeah. Looks like that. It's when it is attached to a surface. But the surface has to be, they have a special surface where they attach it and then they test it there. And since we use it when it is mounted, so this is kind of useful. Mm-hmm. Mm-hmm. Mounted is when it is attached to the surface and then they measure the natural frequency, I think. What is important is in these charts to see up to where it is equal to 1. Honestly, I never had to deal with mounted versus not mounted. Typically what you want to know is when up to which point you can use it. And sometimes, for example, for the cases like that we are looking for, we are willing to compromise and go to higher frequency at the loss of amplitude. So this becomes very important. But the natural frequency, etc., normally you don't. What they have here is what is useful for applications, and it is mounted, I think. Yeah. Well, there is no other resonance, so it's just that's the resonance frequency that they measure. Any other questions? So now let's look at the homework. Let me return your homework. You see that I have given some of you extra credit if it was very. I want to make sure that I So if you have to go to the seminar at 4, that's fine. Continue talking about the solutions. And then you need to ask me questions. So the first problem, I think most of you answered this right. So a few people made a very strange mistake, and that these signals, the first column was time, and the second column is signal. So if your plot, and then I think you have used the first column to do FFT, and that's why it looks very strange. That's just time. So, yeah, I don't know. Is there any question about this? I think this first part is simple. Oh, I also have this solution actually, because I don't post the solution. That's how the signals look like. The spectra looks like. I don't know. There is nothing much to say about this problem, I think. What everyone had maybe a little bit of a struggle was more in interpretation. So one thing that I want everyone to note is that power spectra and a spectra you normally plot it in a log scale. So to be able to see everything, you can plot this in log scale. And half power bandwidth is not an amplitude, it's a bandwidth that is in frequency. And what you see here are like the lines which mark the half power line. That means what is the frequency range that is basically that is between the peak and this line. That's the half power bandwidth. It's not an amplitude. There was a couple of problems. Some of you did very well. Now, how do you get this accurately? That's something you have to do in the second homework. This time I didn't take any point off or anything. If someone had done it, I put an excellent, a smiley or something like that. But so the way to do it, of course. I saw that some of you have zoomed in and got the number. That's all it is. So the way to do it is to use a function in MATLAB called find. So you know how much this is. This is the amplitude over square root of 2, or power over 2, half power. There is a function in MATLAB called find. You can find the points which are just below or above that line. It's a very useful command called find. It gives you the indices of the points which are just below and above, and you interpolate between them. Someone had used a function called power bandwidth. I am not familiar with that, and I honestly I don't believe that is correct, but you never know. If you found a function in MATLAB someone else has written and works for you, voila, that's nice. Use it. But it's important to kind of start playing with MATLAB a little bit more. Does anyone have any questions? It's now a good time to ask questions if you're not sure. Yeah.
Can you write out how you use find functions? If you're going to be looking at half the power value, but I guess I'm just not quite understanding how to find functions to go on to.
No, just look at the help of MATLAB.
Yeah.
So it's just how, if you could find this function equal to, I think I've written down in some of your, so it's like find, if you have your FFT equal to, let's say FFT over a square root of 2, something like that. You can, yes, you can say greater than. Then it gives you the first, and then you look at the maximum. It gives you the first index. You are familiar with that, I'm sure. Chas. You use, it's a very, very useful function. If you see you have a lot of issues or trouble, just come in to my office, I'll show you how. But try to see if you can use it as a next step. But as I said, those are details. In terms of, for whatever reason, I don't know, most people didn't compare the widths of the spectra. It's probably because you couldn't see it. You plotted it for the Nyquist frequency and it was not visible. So it's always good to zoom in, to try to limit the access such that you see most information generally. And looking at data is a very good thing to do. Just looking. Okay? But this problem was, most people didn't have issues with. Yeah. Oh, this one was a problem where, yeah, so here we have velocity and acceleration. Some of you just wrote down how to do velocity acceleration, that's fine. And some of you forgot that you need to normalize it by dt, that's velocity. In the time domain, this is how it works. And in the frequency domain, velocity is always like I omega times displacement. And acceleration is negative omega squared. So the amplitudes become larger. Most of you had acknowledged that. And you had talked about phase being, saying that the phase of velocity is 90 degrees and the phase of acceleration is 180. Of course, the frequency doesn't change because it's I omega t and it will be I omega t. But the amplitudes change because velocity is kind of omega times in terms of amplitude displacement, and acceleration is omega squared. That's why it becomes larger. And if you had plotted the phase, you would see very nicely what happens around this frequency. That the phase of the signal and acceleration are 180 degrees apart and velocity is 90 degrees. As it should be. Some of you have written it down. Some of you know. Some of you have written down that the maximum corresponds to 0. You have reasoned it. But basically I wanted you to see that how velocity and acceleration, how the phases are different, how the frequency of course stays the same, because you remember ei omega t, the derivative is also ei omega t. So it's not going to change. If you have questions, please ask me. Then the noisy signal. This one, most people have done this right, and there is no correct answer. Like, depending on how you define noise, you would get different things. I wanted noise to be the noise that you added to the signal. Right? Something to remember is that signal to noise ratio, you are comparing, let's say, the variance of signal plus noise to noise. Not just signal to noise. That's like your signal. Noise is inside. Here I have given you the noise, that's the random noise. And if you do the averaging, the signal to noise ratio should improve, should become better. And that's something we do in practice very often. You average the signals because the random noise, it's random, it cancels each other. The maximum, minimum, they just cancel each other. If you have questions, ask me. So this one was among the good ones. That's where I think most of you had a lot of issues, which is understandable. I kind of wanted you to experiment something. Let's look at number 4, everyone together, because almost everyone had at least one issue with that. So we plotted signal 3 and 4. There are 2 pulses and there is 1 second in between them. Then I ask you to plot the phase and unwrap it. When you unwrap the phase, it looks like that. The function in MATLAB is called unwrap. And That's, some of you have gotten to this point and then didn't go beyond that. So the phase delay time is the difference in phase divided by frequency, not divided by sampling frequency. The difference in phase, as you can see, is a function of frequency. At every frequency, this is your phase delay. That's at this frequency. At this frequency, it's this phase delay. It's so if you have you have 2 pi phase between 2 signals, that's like 1 period. Time delay. So here is phase, here is time. If you have delta phi, how much would be the time delay? It would be delta phi times t over 2 pi, or it would be delta phi 2 pi f. Another way to think about this is what I have shown you in the very beginning. When you have a sinusoidal, basically the phase delay is this, and it's just phi over omega, which is again phi over 2 pi f. So when we talk about phase delay, this is what we mean. And it's a function of frequency in this case. And if you divide it point by point by the frequency, you should recover the same 1 second that you have in the time domain. I wanted to show you that you experiment that you can use the phase of the frequency spectrum to get the time delay in the time domain. You may think that why it is useful. Why wouldn't we just look at that and this is 1 second? The reason is that there are waves which are dispersive. They have different velocity at different frequencies. So if you look at the frequency domain at a certain frequency, you can get phase velocity. You cannot do it in the time domain. Again, I explain this one more time because a lot of you do not got to here, but to here I think no one actually got this. And you argued that, oh, in the time domain it's 1 second and we don't see any difference in the frequency domain. And if I didn't know with the exclamation mark, sorry. So I was like, no, you can see it. It's different. You can see that phase is changing. So again, these are 2 pulses. One is just 1 second ahead of the other. So we looked at the frequency domain, amplitude looks just the same because it's the same pulse. But in phase, their difference shows up because one is lagging behind the other one. When you take the phase of the Fourier transform and you unwrap it, you see one and the other. And you see that with frequency, the phase difference between them grows. Okay. Now, to get the time delay, you need to divide this by the respective frequency. So if you, when you have this change of phase, you have to use this in MATLAB. It's a point before the slash. That makes it point by point. Then 2 times pi times f. And then you would get a straight line nicely like that. You can even kind of see that it's growing linear in frequency. So if you divide it by frequency, it will be constant. Now, the reason for that is that this is one way to measure the time difference. It is useful for waves which are dispersive. There are waves which different frequency components have different velocity. So you need to do everything in the frequency domain. So you look at every frequency component and you do the same thing, and then you have to start it. Okay? But it's fine. I haven't even taken, I think, just maybe a couple of points. It was very easy. 5A is in the lecture notes. This was free points for everyone just to go and grab. If you don't know where the lecture notes are, please talk to me. They are in PDF on Canvas. All you needed to do was to look for that. Is everyone listening to this? And like half of the class didn't write this down. So just to make sure that you know where those things are. Yeah, so if you change A, you are going to get a wider, if you, a smaller A means a wider spectrum. I think everyone has done a reasonable job to describing this. This was kind of easy. And then here, surprising to me, there were issues with this. I guess maybe the question I have to rewrite it, rephrase it. So here I wanted you to create the same half sign yourself digitally. So using two different sampling intervals. To create this half sign, just if you look at the equation here, this is not a sinusoidal, it's a half sign and then nothing else. So you needed to create this digitally with two different sampling rates and plot the spectrum. Now, something that a lot of you haven't done is not having read this hint. Where is the hint here? When you do the FFT, where you care about the amplitude, you need to multiply your amplitude by the sampling interval. That's why your amplitudes don't match the analytical solution. If you look at MATLAB help for FFT, it's even written there that MATLAB calculates as if the sampling interval is 1. It never multiplies it by dt. So that's why. But I put this hint here because I knew that probably you didn't pay attention, this was not important. And most of you did not read this hint. So if I have written in your notes, it was written in the hint, or look at the hint, that's the hint I mean. If you did that, the analytical solution and the two digital solution, they would kind of be like this. And the higher sampling rate would be, of course, better. It's nothing very hard or anything like that. This one, I think most people did a nice job. Some of you did not plot the spectrum. I don't know why. So the function is such that it actually goes on to 2 times 150. That's how the MATLAB function works. And here you can see how the frequency is changing linearly with time. Here I just wanted you to understand how to use a spectrogram. There are details about CHIRP, why it looks like that, because there is a lot of manipulation with the phase of the components inside. That's why it looks like that. But that's not really important for the purpose of this class. So please look at your homework, see that I haven't made any mistake or anything like that. And then I enter the grades in Canvas. I hope that you had a chance to look at things.